Swayam Prabha. Digital India. Educated India.
In the last class, we were looking at brush model, right? And then we moved on to what we called as a magic formula model, which is due to Pacheco, right? And we saw that basically the first model that was put forward in the Pacheco model, Tyre model, is to fit the experimental curves that were obtained during Tyre testing, right? And we will now slightly go into the details of Tyre models before we, I think we have to quickly go to the lateral dynamics. We won't have time to go into completely the Tyre models. There were some questions on, in fact, what happens during combined slip. We will spend a few minutes on combined slip before we go to the rest of the topics, including the Tyre model. But there were a lot of questions on Tyre models after the class, so let me explain this. This is from a paper in vehicle dynamics, vehicle system dynamics. This is the reference. It's a very nice figure. Volume 43, supplement 2005, 18 to 29, Alex Eichenberger and Marcus. So this is the this is a paper, just there's a reference for this, and let's just quickly run through this so that you understand what we mean by Tyre models. As I told you earlier in the class, we started that a lot of codes that are multi-body dynamics codes that are used, and multi-body dynamics becomes extremely important because of the fact that there have been a lot of companies use it, and that the companies look at how to optimize the vehicles and so on, right? So they use a number of softwares. The software that is used, okay, depends upon the reason or why they use this, or in other words, it is not one comprehensive software and one comprehensive model, but there are a number of models, and the models also depend upon the reason for which they are doing an analysis, okay? And a part of it is the Tyre model. Please understand that we are looking at dynamics of the vehicle. We are looking at oscillations, be it cornering or be it ride or whatever it is, we are looking at oscillations. And the oscillations or the frequencies of oscillations that we are looking at covers a whole huge range, okay? And the models that you put in should be able to simulate, okay, or get you the results in that frequency range. Clear? So there is a frequency range and an amplitude. Yeah.
So what do you exactly mean by vehicle oscillation? Is it like for the sprung mass or?
Yeah, we will come to that a bit later. But before that, okay, let us understand. Yes, I understand what you're asking. Let's look at this figure. Then you will see what we want to say. Okay, so the vehicle oscillations can be classified in terms of frequency of oscillation, okay, and the amplitude of oscillations, right? So yes, when you talk about oscillations, immediately you think that there is going to be a bounce. You know, a vehicle goes over a rough road and you see that bounce and so on, and immediately you have a tendency to sort of map this word oscillation to a vertical oscillation, right? But it's not necessary that it has to be vertical. That's what we're going to see now. Okay? And you will see that when we talk about oscillations, it covers a gamut of things, right? It is like the whole electromagnetic spectrum which we talk about when we talk about light, we talk about sound and so on. Like that, you have a number of, the whole gamut of things that we're going to look at, various frequencies and amplitude, right? Okay. Now, at the lowest end, we look at what are called as quasi-static models, where we study the suspension kinematics. Okay, you had studied, say, for example, 4-bar linkages and so on in your earlier class on mechanisms. So you use that kind of concept to understand actually when you give a steering input, how, say, for example, the steering linkages move, okay, what is the arc that it covers, and all those kind of things. Okay, so you use the fundamental concepts in theory of machines or kinematics of machinery which you studied in order to understand that. Okay, so that's the quasi-static models, right? The amplitudes may be very large because you're looking at when you turn a steering, how things move and so on. And many times the models that you use for a tire, in this case, is a finite element model, simple static finite element model and so on, right? Okay, we'll come to this tire models in a minute. Next in the range, look at this, this amplitude can be large. Next is what is called as the handling models. Handling models. Please note, models simply means equations. Next, we talk about handling models. We're going to do that from this class, maybe starting from next class, right? We are going to look at the forces that are acting, the accelerations, and so on. We had already seen this for the longitudinal case. Handling is more to do with the lateral forces and the lateral dynamics, and that we are going to see as the next step. And so we are going to look at handling models. In these cases, as you are going to see now, you consider the chassis as one rigid body and look at how, for example, the chassis is going to yaw, or the body of the vehicle is going to yaw, is going to roll, and so on, right? So we do not go into the details, and usually this kind of models look at a picture where we look at the whole chassis as one group of components. Yes?
So why does the frequency change for that?
Yes, good question. So what is that we are looking at there? We are looking at various frequencies. You will understand that. Because this depends upon, see, when we look at handling, it depends upon the frequency of the whole vehicle, okay, of the vehicle at various modes, or in other words, in various directions, in simple terms. Okay, you would see that we will come to this handling when we take a turn. Okay, you would see that certain frequencies, okay, which are the result of the whole of the vehicle mass, moment of inertia, and so on, are going to have a role to play. Okay, and those frequencies are in this range, Okay, the frequencies which are going to play, okay, when we look at lateral dynamics, handling is about 4 to 5, 3, and maybe 2, 3, 4. That's the range.
So, but the lower frequencies will also be there, right?
Yes, of course. See, the point is this. Is it that I'm neglecting all this? No. What we are saying here is that we look at different frequencies to look at the effects. Okay? Look at the effects. For example, if you're looking at noise, yes, you may be cornering, maneuverability. If I am looking at maneuverability of the vehicle and so on, the frequency range I am looking at is this. But at the same time, I'm looking at the NVH, the vibration characteristics and so on, and then I would comfort, for example, I would look at these frequencies. I am looking at actually acoustics, okay? I would look at higher frequencies. It is the vehicle is moving. It's that you are artificially distributing it at these frequencies and studying the effect, okay, at these frequencies. Go and study. When I say that, go and study the frequency at this range, which means that you are looking at handling, and that's the result of the characteristics of the vehicle when it takes a corner. Right? And the ride, for example, the next set of frequencies that you are looking at is the ride. Please note, why am I saying this? Please note that the model should be capable of representing the vehicle in these frequencies. It should be able to represent the vehicle in these frequencies. Okay? Suppose you take a simple model, what we are going to see, for example, bicycle model for handling. Okay? Then, if you tell me that I want to study the acoustics, okay, with this kind of model, you won't be able to study it, okay? Because it will not produce the kind of frequencies, the natural frequencies of modes or whatever you call it. We're going to give some names to it, okay? These things will not be represented by that mathematical model, okay? So there is no point in having a simple model which we are going to say, study, and say that I'm going to study this, because that model will not represent the behavior of the vehicle at these frequencies. Does that point make it clear? But as a vehicle, yes, as a vehicle, it has various spectrum of behavior as a vehicle, okay? But many times I won't be able to take everything together and start working. And my interest also may not be on all these frequencies, right?
Does this hold good for all vehicles or?
No, it holds good for every vehicle. It is not.
Say heavy vehicles.
Yeah. Okay. The frequency range may be this side, that side, but it's around less than 10. Okay. Let's look at the next set of frequencies. I'll take the question after I finish this. Okay. Then we'll look at the next set of frequencies. We are looking at ride. Okay. Looking at ride. Ride usually is divided into two categories. Okay, one is what is called as the primary ride, and the other is what is called secondary ride. Purely in terms of the frequencies. The lower frequencies at 10, 12 hertz, okay, you would call this as a primary ride. Okay, people vary when they define what is actually the primary ride, what exactly is the frequency, and so on. But usually we will look at the primary ride as one due to the oscillation of the suspension system. Okay? This is because of road-induced oscillations and so on. 10, 12, 14 hertz is the type of frequencies that you would call when the vehicle is subjected to these kind of oscillations. Okay, at those frequencies, we call that as the primary ride. But then, ride is a topic which is not only affected by, note this carefully, that is not only affected by the road. Okay, today ride encompasses a much larger things. Okay, so for example, there can be oscillations of the engine, transmission, and so on, which may be at a much higher frequency, maybe about 30 hertz. Okay, so there may be oscillations of the engine, okay, which may be transmitted, and your engine mounts may not be very good. There may be transmission of oscillations due to engine, and so on. Okay, then the frequency of excitation due to these factors will be at a higher level or higher frequency, and that is what is called as the secondary ride. Right. Then comes harshness, okay, what we call as loosely as NVH. That's comfort. Okay, that's at a higher frequency, at a much higher frequency. So, in fact, if you look at the total ride, how comfortable I am in the vehicle, then it actually covers the whole thing. Okay, you can also see that as I go down the frequencies, actually the amplitude comes down. Very well known case. Right, the amplitude comes down. Now you move to a much higher frequency, okay, which is above 100 hertz, okay? Strictly speaking, going up to 20,000 hertz, but we're not interested up to that because that is the acoustic range, but 20 to 20,000. But we're not interested in that kind of large ranges, but the acoustic frequencies, which is of interest to us, may extend up to about 2,000 hertz. Yes.
What are the quasi-static oscillations you are interested in? And
The
how
quasi-static is where I am looking at the suspension mechanics or mechanism, okay, steering mechanisms. So suspension, kinematics, steering, kinematics, and so on. Yes, so these are oscillations, okay. These are, when I take, say for example, when I give a steering input, okay, how does actually, what's the range to which this the steerings has an effect on the wheel, and that whether Ackermann steering is completely followed or there may be error, what is Ackermann error, scrub radius, all those blah blah blah, all those things. No, they are not. That's why we are saying that it's at a much lower frequency. That's why we call this as quasi-static, very near zero. Though it's not actually static, we call that as quasi-static. So, okay, right. We will come to that. You know, these are frequencies when the vehicle is subjected to that kind of frequencies. Okay, the frequency that whatever happens in that frequency range, we call that as NVH. It's just for us, okay, to understand and give a name. And I'm going to talk why we have done this as well. Now, I have to have, these are the frequencies at which I'm going to study. Okay, I have to have models, as I said, which will depict the behavior in these frequencies. And one of the most important model here is what is called as the Tyre model. The Tyre model. Okay, let's go to the extreme range. Yes.
Sir, I mean, you mean to say that in vehicle these all frequencies are available, and at each frequency these
Yes,
are, this is the
yes. These are the frequencies, okay, which will excite the vehicle, various components of the vehicle as a whole, or various components of the vehicle. Okay, we will. Okay, good question. Let me go into that with the Tyre model. Let's go to the extreme case. Okay, now I want to study noise. Say, for example, I want to study tire noise. Okay, which means that I'm looking at frequencies which are above 100 hertz. Okay, yeah, that is where the usually that's a big topic. Usually the range, usually the range of hearing is from 20 to 20,000 hertz, and very interesting factors have come about. Like for example, your ear is very sensitive to frequencies of about 1,000 hertz. Okay, so that's where you're very sensitive to this, and so there are the magnitude of noise, okay, expressed in decibels, are now adjusted, and you have scales like A scale which adjusts to the sensitivity of your noise and so on. So you are sensitive as a person. See, you perceive vibration, okay, due to various parts of your body, right? I mean, so in fact, we will see later when we go to ride dynamics, okay, the last part of this course, where we will look at ride dynamics, we will look at what is the amplitude which your body can withstand without fatigue, how long it can withstand, what is the frequencies, and what is the corresponding amplitude, for example, how much you can tolerate. All these things, we would look at it later in the course. But if you look at acoustics, what your ear is sensitive to, those frequencies are about this. Okay, your ear is very sensitive to frequencies. That's why you are able to enjoy music whose frequencies, okay, what we call in Indian classical music as swara. What is that? There's nothing but the frequency. Okay, it comes from the Archimedean principle of dividing the frequencies into different octave and so on. Let's not go and get into those details. Let's look at this model. You know, let us come back and look at the models. Okay, now. To answer this question, like we are looking at acoustics, let's see actually physically, that's been a practice in this course. So I have a tire, okay. Now the tire goes over some rough surfaces, that's all of us know. Then the tire, we saw in one of the earlier classes, say for example there are belts that are available in the tire. Okay, so the belt starts now vibrating. It is something, you know, you've done some course in mechanics. It's something like a shell, okay, stiffened shell or an orthotropic shell, okay, that starts now vibrating because it has gone over a rough surface, right? So when it starts vibrating, let's say that it vibrates like this. It vibrates like this, okay? Now this vibration of the belt, okay, which is actually the sum of various modes or mode shapes of the belt, okay. Now this vibration of the belt, what does it do? It has it displaces, so it starts vibrating like this. So it takes a inner and an outer shape, goes up and down. So when it goes up and down like this, what does it do? It excites or passes on this to the air okay, molecules which are near this. Okay, that's one of the things. So it starts oscillating. So the air molecules near it gets, into this oscillation. In other words, pressure changes, and this acts as a source, okay, for the pressure change. And at certain distance, you hear that as noise because these guys are displacing the air above and below, and then that's the pressure wave that starts, and that's the source. That's one thing. The other thing is that when they vibrate, okay, when they vibrate, they also change the forces that are acting, or in other words, if you now plot a force or acceleration at the axle level, they also change. Okay, so in other words, with time, the accelerations change, and these accelerations now start, okay, traveling inside the vehicle, and if you are sitting in the driver location, you're going to hear that as well. So in other words, the noise that is produced, okay, passes on through the air, and from the air, maybe it is translated or transmitted to the door, and it starts oscillating, and you're going to hear all those noise. So tire, for example, tire noise can be classified into what is called as the airborne noise and this structure-borne noise through the axle, and gets it inside, and then you hear this. Now, if I have a model, since you asked this question, now if I have a model which cannot actually capture this kind of belt vibration, what we are looking at is also a brush model, simple model. Now, I'm not able to capture this. Then, whatever I do, obviously, I won't be able to capture noise. Hence, that is why models become important. So what model you use? Unless I have a model which I'm able to capture this, which is the source of vibration or excitation at that frequencies, I am not going to produce that frequency in order that I hear this, right? Okay, so our simple brush model, for example, will be enough to do things here. But then I need to keep innovating and improving it in order that we do it further. Yes?
Why are we interested in only sound and noise characteristics?
No. I am not saying that why are we interested in noise. I'm saying that noise is one of the factors. Okay, it's not that I don't want to make too much noise, right?
But if we consider some other effects of vibrations, then maybe 10 hertz and 1 hertz also will not.
Yes, every frequency is of interest. Okay, so if you're going to make a car and sell it, okay, you are going to be worried in this whole spectrum of frequencies. Your car is not going to sell if you say my handling is very good, but only thing is you can't sit inside, the noise is very high. Right? Oh, the engine noise is very high when you sit inside, but I can handle, my car handling is very good.
So every component.
This won't work.
Even the engine would have vibrations corresponding to.
Exactly. So at different frequencies. So that has to be now taken care of, isolated, so that you do not hear or you do not feel whatever is your sensory perception is, of these frequencies. This is very important to understand this. Yes, this is well-known fact in the industry, but your students, it's very important that you understand, okay, what we are talking about. And the macro picture is extremely important for you to appreciate the course on vehicle dynamics. Okay, I would have given this first, but you wouldn't understand. Now that you know what is a tire model, now you know you are able to understand that very well. Okay, so this is very important for us to look at, right? So the tire models that are used are now different at different in the different frequency ranges. You have today a set of tire models which can handle different frequencies. Okay, you have, for example, a model called Swift model. The name itself is like that: short wavelength intermediate frequency tire model. Right? So that may be about 70-80 hertz, and that's the frequency which it can accommodate, and that's what you see here. So most of these models are, yes, we saw an empirical model, but there are semi-physical models, as they are called. In other words, the tire is modeled as consisting of a number of springs, okay, mass systems, and so on, and that approximates the behavior of the tire. We won't be able to go into the details of it. We have another course actually on tire mechanics where we would talk a lot more about tire. We are not going to do that in this course, but I want you to understand where we talk about and what we talk about and what we are looking at and so on, right? So this is what is the importance of tire models, right? And this, what we call as multi-body dynamics. This is multi-body dynamics, the range of multi-body dynamics applications. Also looks at the dynamic loads, the effect of dynamic loads. For example, when you come to automotive structures, you would look at this carefully. You would look at dynamic loads. What is the load that is transferred, for example, to various parts of the vehicle, for example, to the chassis frame? Okay, what is the effect of this dynamic load? Its effect, in other words, what is the durability? And all those things also will be studied. What's beyond this is what is called as crash. Okay, crash is crash covers a gamut of frequencies. The very high frequencies and amplitudes are also very large. So that's the crash part of it. Okay, it's a nice picture. It gives you the whole thing. And let's get back to what we were doing in the last class. Right.
Quasi-static, you told like since it's low frequency, it doesn't affect you. So say, for example, if you take handling, you said yaw, how does it affect?
Yes.
Change with frequency?
You have to wait for some time to get an answer. So what is handling? What is yaw? How does it have an effect? All those things will be studied in this course. So in other words, you will get into models here. Okay, I won't be able to get into these models beyond this, but I will get into models which cover this and this. You know, these parts are part of this course, so you have to wait for some time in order to understand, you know, what do I mean by the second thing, right? We will do that.
By frequency, we mean at particular instant, different components has different frequency, right?
Yes. So different, it's not different component of the vehicle. You know, this is, we are talking about the vibration of the vehicle, okay, induced due to various components. Okay, for example, when you are looking at the primary ride, okay, you can treat this whole body as a rigid body, and we are going to look at that as a rigid body, right, at those frequencies. So in other words, the frequency is dominated by the spring dashpot system of the suspension. Okay, so when I go to higher frequencies, then there are contributions at higher frequencies, and that may be due to bending of the chassis frame. Okay, so in other words, the source for these vibrations and the way they are transmitted and so on, okay, would be different, right, at different frequencies. So for example, when I am here, I am looking at the body as a whole, controlled by the suspension characteristics, right? Wait for some time, you will understand more about this as we go along.
Sir, how do
Okay.
you know at the low set of frequencies, the suspension will be predominant? How do you know that the suspension kinematics?
Yeah, we are looking at suspension kinematics. We know handling is affected by these frequencies. So wait for some time. We will come into those things. Okay, we will look at these things. Why am I looking at this frequency? Why is it? Because this frequency, when I take, for example, when I take a turn, and we're going to look at this from a very simple bicycle model, and then if I take a turn, then the frequencies which are excited, okay, is in that range, right? Okay, we are going to look at the mathematics behind it, and then we will understand why these frequencies are. Why this frequency of 12 hertz? Okay, you will see that there is what is called as a wheel hop frequency, and the wheel hop frequency is 12 hertz. You would understand that there is a body, the frequency of the whole body, that would be at 2 hertz. You have to wait. Please be patient to understand these frequencies. Understand this alone, that vehicle as a whole has a gamut of frequencies which can be excited. Okay, which can be excited, and so you have to understand the behavior of the vehicle at all these things. In other words, just to complete this, it's not that I have to excite all these frequencies. In other words, I can isolate frequencies, okay, by different means at different levels. For example, I can isolate completely the noise due to the engine. There are ways and means by which you can isolate this noise completely. But that doesn't mean that the technique that I use in order to isolate this noise would make my handling better. So you have to look at what you. So the idea of studying this is because the solutions as a design procedure or a design problem is different at different levels. So when you say that this vehicle, in other words, when you say, simply put it, when you say that this vehicle handling is fantastic, but my ride is not very good, or vice versa, okay, what is that you are saying? You are saying that the vehicle behavior, or you are characterizing the vehicle behavior at different frequencies. That's all. Okay, you're characterizing them. That's it. Okay, let's move on. Let us now look at combined slip. I'm not going into the details. I thought I would do it, but I think we are running out of time. We have to move to the next topic on lateral dynamics. I just want to point out that when we have combined slip, we are looking at longitudinal as well as lateral. Okay, both of them are acting together. Okay, in other words, the forces in the longitudinal direction and the lateral direction are going to now compete with each other in order to win over the mu into F or Fn, right? So if I now plot, say for example, the force, Fx and the force Fy, okay, if I now plot this graph, this would, okay, because of certain reasons of anisotropy and so on, would become an ellipse, something like this. In other words, what it simply means is that this is due to longitudinal, say, braking or acceleration, and this is due to cornering. Okay, when I do a cornering without any lateral acceleration, I'm going to get the full benefit of my mu. This is the boundary after which, okay, it's going to stop, and after which I've reached the mu into Fn, or I've cashed all that is in the bank called the friction forces. So once I do not have any braking or acceleration, okay, that is the complete force that can be used in order to generate Fy. And that's the end, okay, where I would generate the complete, or I would use the complete frictional force in order to get this. Yeah, because this is nothing but the force, okay, qx plus qy squared, okay. That's the force. Say for example, force per unit length should be less than equal to mu into qz. Per unit length is what, you know, qz is the normal force per unit length, okay. And if you give it like this, actually it should be a circle, but qx and qy need not be the same. You know, like what happens in the longitudinal and the lateral direction forces, that need not be the same, because it's the forces are split in the ratio of the slip and so on. So the practically this wouldn't be wouldn't be a circle, but it would be a sort of a distorted ellipse.
So this kind of implies that the boundary, the mu and value is kind of different for fx and for fx.
Yes, yeah. So that is because the way it is shared is different here. So ultimately, say for example, if you are doing both cornering and braking, that is the type of forces that you would generate. Yeah, this is the fx and fy.
The major axis is
See, this is an ellipse like this. So you can say that that's an ellipse like this. Okay, so I'm putting only the one part of it. Actually, the qx and qy is given by, I'll just write this quickly. When it is in the slipping region, per unit length, I already said that, force per unit length, okay. So, and you can derive this, and I'm not going to, as I said, go into the details. You can look at Pacheco's book. So derive this same way as you had done it for the longitudinal force. Now include longitudinal and lateral force, okay, and then you can derive this, and the fx now becomes, look at that, I'll quickly indicate after this how we got this. That is fx. Just a minute. Let me finish this. I'll explain it. Let me write down this equation, and I'll explain this. And this would be your assignment. How we're going to get this. Though the expression looks formidable, it's not very difficult to derive this. It's quite simple. This is into sigma x, sorry. That is the whole thing multiplied by sigma x. The whole thing multiplied by sigma y, and m is at Okay. So essentially, what is that? What's that you do? Essentially, how did you get this? Well, there's too much of noise. That's going to have an effect. Yeah, essentially, how did we get this? We got it in the similar fashion as we did before. Remember, how did we get this kind of expression for a longitudinal force? We looked at the deformation. Okay, you remember that we looked at the deformation. We looked at how much the thread, which was a brush, deform as you move into the contact patch. And then at a particular point of time, we said that the force is not good enough to sustain the frictional forces and it starts slipping. This is exactly what you would do. You would now look at the brush movement both in the x direction and the y direction. So the brush movement in the x direction, so you define sigma x and sigma y as given here, and you would, this is exactly what you did previously into sigma y. Now, which now becomes the basis for the force. In other words, these are the displacement of the brush. Remember that we looked at the brush, okay? In the brush model, we had those brushes. So now, please understand that there is going to be a longitudinal as well as a lateral, right? Both are acting. So the brush, the bristle will actually be displaced in the x direction as well as in the y direction. This is a displacement, right? Go back and look at it. This is what we did before. This displacement would result in a force which I would call as Qx, okay? And the force is because of this displacement multiplied by the stiffness Cpx in the x direction. Displacement multiplied by the stiffness per unit length, gives you the force per unit length. So that would be Cpx into A minus x into sigma x, and Qy is equal to Cpy into A minus x into sigma y. Right? These are the forces. Now, when it slides, root of qx squared, that is this whole sum of these forces, okay, should be equal to mu qz. So in other words, the sliding distance xs is determined by root of Cpx into A minus xs into sigma x, okay, this whole thing squared because qx squared plus cpy into a minus xs into sigma y whole squared is equal to mu into qz. Remember qz, we got it from the parabolic distribution in our earlier class, so you can substitute for qz, solving which you will get xs. Then what do? You find out the total force, okay, because of deformation plus sliding rather. So the rest of the region, it is going to slide up to xs, it is going to stick, deform, after that it's going to slide. Try this out. If there's any question, I'll answer that in the next class, okay. Please try this derivation, see whether you get this. It's not very difficult because you just want to add, then integrate it, and you're going to get this, okay. So we will not go further on this unless there is a question which I'll answer in the next class. Try this out, okay. Fine. Now we now know that a combined slip is more dangerous because whatever lateral force that's required is not given. Becomes dramatic in the case of motorcycles. Gives rise to what is called as high side fall. Okay, it becomes really dramatic. So in other words, when you take a turn in a motorcycle, you're braking the motorcycle and suddenly release the brake. We'll explain that maybe in the next class, starting that, so you will understand lateral forces. Suppose you're taking a turn, braking, and suddenly release the brake. What really happens? Now, it's a very sharp turn. Young blood going fast, take a sharp turn, right? Suddenly you see a kid coming across and just press the brake, okay? You're still taking the turn, and then suddenly release it. Situation is very dangerous. Why is it? Because when I brake it, think about it, we'll continue that in the next class. Okay. When I brake it, I am at this position, sudden braking, right? When I release it, my fx now comes to 0. Okay, immediately fx comes to 0. But my fy is not the same as what it was before. Fy now actually increases suddenly. So in other words, whatever friction which the longitudinal force was holding now gets transmitted to the lateral force. So lateral force becomes high. Lateral force should be just enough to compensate for my centripetal acceleration. But lateral force becomes high, whole vehicle, okay, turns overturns. We'll explain that in the next class before we go to the lateral dynamics.